So yeah, hi everyone. Thanks for coming. I'm gonna talk to you folks about this new treat package I've been working on since a while. So I'm gonna do a bit of intro rambling and how the workshop works and everything. But while I'm rambling, you can try to install the package if you want to follow along with me, or if you don't want to, if you just wanna, it's Friday afternoon for some people here. So if you just want to relax, sit back and just listen to me talking, it's fine. You don't have to follow the workshop by copy pasting because all the materials are online and you can go through them at your rhythm later on. But if you want to do copy pasting alongside with me, I suggest you install the package now while I ramble about treats. So just to start, this package, although I have been the main person developing it and I'm the sole author on the paper, I do want to insist that it's definitely not something I do alone. A lot of people have helped through many stages of the project. Hopefully, I've listed most of them here. But yes, so of course, I love collaborative science and all these things. So yeah, so what's TREATS? TREATS stands for Trees and Traits Simulation. The pun was suggested by Chris Cooney. So thanks, Chris. That was very good. And basically, what can you do with treats? The package is built in a modular way so that you can basically do anything you want. Normally, I haven't tried to do everything yet. So of course, there might things that are more difficult to do than others, but basically you can use this package to simulate either phylogenetic trees or phylogenetic trees and traits that can be used, for example, if you just want to illustrate some things. I don't know, for teaching, you want to illustrate some kind of models of evolutionary models, things like that. You can use it for that. You can use it for developing some toy models, for example. This depends on how you work. I know I work a lot by kind of drawing my kind of expected outcomes and stuff like that. So rather than do it on paper, I can use the treats package. Another use of it is to simulate kind of more complex no evolutionary models or neutral models. I'm going to talk in more details about that. But pretty much the package is designed so that you can do whatever you want in a rather easy and repeatable way. We're going to go through some ways of doing that, and hopefully you'll get the gist of how the package works after this workshop and you get excited to use it for your own project. So yeah, just for starting just also on how I'm going to do the workshop. So I'm going to be, when I have this white screen here, I'm going to do some rambling. So basically general kind of thoughts and discussion. Then I'm gonna show at some point, I'm gonna show some copy pasting codes in R. So here I use Sublime text for as a EDI. You can use RStudio directly, whatever you want. This is basically code here. And this is just R. Let's see if everything works. If I do this, yes, this works. And I'm gonna see some plots as well on this screen as well. But for now on, I'm just gonna go through this thing. So this is the HTML the HTML file. So the last of the three links that Natalie has shared, and this one here, this file here, this is the first or the second file that Natalie has shared in the chat if you want to follow along. Again, if you don't want to follow along, don't worry, you can just listen to me and watch your screen. This should be enough. So things you can do in treats, for example, this is an example directly from the package where I've been basically simulating a tree. So here you have time in arbitrary time units. So that can be millions of years, for example. Here's some traits that I called A because it's very descriptive, and some trait values. And you can see these orange dots here are nodes. The light blue dots here are extinct species, so fossil species, for example. And the blue dot here are living species. So basically, you can see here this trait and tree growing together through time. And in this simulation, I've coded a specific way that after half the simulation, so after 3.5 million years, let's say, extinction rate drastically increase for species with negative values. So you end up with this tree here, with this region, with more extinct species. So this is an example you can do. Here is an example. I mainly like it because it's in 3D and it's spinny. But this is basically a tree simulated with two traits that are at the start. So you have time on this axis and your two traits, A1, A2 on these axes here. And you can see at the start of the growing of the tree, as you can see here, I made both traits completely correlated. So both traits have the same value. And again, after some time, I decrease the strength of correlation, and this results in this kind of, smudge kind of correlated pattern for living species. So again, this is relatively easy to do in the treats package. This is another example. So yeah, I was kind of hoping to release the package around Christmas, but that didn't happen. But you still get a Christmas tree generated through the package. And yeah, in the UK it's so freaking cold that it feels like it's still Christmas sometimes. So there is that. But yeah, basically in this kind of simulation, a little exercise, every million year, I'm basically making going extinct all species on the edges of the trait distribution. So these species go extinct, these species here go extinct, and these ones go extinct, these ones go extinct, etc. It gives this kind of pattern. Tree-shaped, like Christmas tree-shaped pattern. So sorry for the people that were thinking about like a dendro workshop or botany. This is the closest to a tree you're gonna see, but it's green, so it counts. So yeah, another kind of more serious use of this package could be for example, developing, as I said before, no models, no evolutionary models. So in this example, I'm just going to use a subset of a data published by Robin Beck and Mike Lee in 2014. It's basically looking at mammalian traits around the dinosaur extinction, the KPG extinction 66 million years ago. So here you have time on this axis, and this is like several species here, some living species, some extinct species, and you have the dinosaur extinction somewhere here. I think it's easier to see here in 2D, so this is just one trait. You have the KPG extinction here, so the dinosaur extinction here, and you have your trait growing through time. This is just a subset of a bigger data set. But basically, for some among you that are paleontologists, common analysis to do with that is to look at disparity through time. For those of you that don't come from a paleontology background, this is basically functional ecology or dissimilarity kind of techniques, where you basically look at the diversity of trait values through time. So this is called here disparity through time. Here I use this metric sum of variance. Don't worry about it, it's not important here, but basically I'm tracking some kind of like occupancy of this trait space through time. So it goes up, then we go a bit around here, whatever. Here you have your KPG extinction. And what you can do with these classic curves is a classic question also always around the KPG extinction is whether, the big asteroid that wiped out dinosaurs, did it reduce mammalian diversity of traits, or which is often more accepted, is this idea that this extinction liberated kind of some niches for mammalians to evolve into. So we should see some kind of increase in trait space occupancy or in trait diversity through time. This is not what we see here, but again, this is an example data set. Maybe we wouldn't expect to see anything. But one question we can see with this kind of, substandard data set is whether our question of did the KPG extinction release mammalian evolution, could we actually detect that by any kind of extinction? So the idea there would be to simulate some mass extinction events and then measure this kind of disparity through time and see if we could pick any signal, even in simulated best case scenario data, and then compare that to our observed data. So this is what I'm going to do here again really quickly. So this is using the treats package. This is a simulated tree where around here, so time goes up. around here, you see I simulated the mass extinction event, and then you can see what's happening with the species that are still alive, their evolution in the trait space. And this is the same one, but like instead of creating a random extinction event, I just created an event that killed basically all species with a positive trait value. And this is the resulting tree. Again, maybe it's more easy to see in 2D. Here is my simulated extinction event that's happening here. So all these species go extinct here. And here's the same one, but I bias for species with positive values. So all the species with positive values go extinct, and I'm left with these species evolving from the survivor. And then again, I can draw my disparity curve through time and compare that to my observed curve. And then you can do some more advanced statistics, for example, rank envelope test, etc. I'm not going to go into details here to compare these kind of disparity curves. So this is basically an introduction of what you could do with the package. Again, you can do many, many other things. Hopefully everybody is still following. And basically, yeah, what I want to do from here on is to kind of show how relatively easy it is to basically design all these scenarios in the package. And hopefully then you can use that for your own questions or just for playing around, etc., etc. So now I'm going to switch to the coding part. So if you're following along, this is where you can start copy pasting with me. If not, it's fine. For those that manage to install the package, you can just do library treats. Again, for those that don't want to do any copy pasting, that's fine. You can just follow along the basics on how it works. Okay. I guess everybody's muted, so I'm just gonna assume everybody said, yay, okay, continue. So the basic needs for growing a phylogenetic tree is basically setting up a stopping rule. So that's so that the algorithm doesn't just generate a tree forever, because that can just smoke your RAM. The way to do that is rather simply is you can create a rule that says, for example, stop when reaching a maximum of 200 taxa, stop when reaching a maximum of 4 time units. So you basically just create a list with a name element that can be max taxa, max living species, max time. And this is just a list that says max taxa equals 200, for example. And then you just feed the stopping rule to the function treats. So this function treats is the main function of the package. This should simulate a tree with 200 species, and this should simulate a tree with 4 time units. So the resulting objects here are just philo objects. So for those that are familiar with the ape package, this is just a tree, how most trees are stored in R. So this is a tree with 200 tips. Yeah, that makes sense because we tell it to stop at 200. And this is a smaller tree with 66 tips that should have 4 time units. So let's visualize that. Okay, beautiful tree with 200 tips. And then this is a tree with 4 time units. So I don't know why there's this rounding thing here, but I think it still makes sense. It goes from time unit 4 to time unit 0 and has several amount of tips. So this is the very basics on how you can build your trees. Of course, you can give multiple stopping rules. So let's say here, I'm going to give a stop rule that's either do a tree with 200 taxa or either do a tree with 4 time units. The algorithm basically stops when the first condition is met, and you can just feed that to your stopping rules and just visualize that. Here we can see the first condition that was met was probably reaching 4 time units. Let's see how many tips are in this tree. Yeah, 90 tips. So yeah, it stopped here. If you change these values, it will change your tree again, etc., etc. So here you can see already a bit of the start of the modularity where you can change these values easier for getting different tree. This is very basic. I think a lot of packages in R allow you already to do that, but so I'm going to build up more complexity here to show the advantages of using treats. So here, basically, I have not specified any parameters for building my tree. This package is using a Birthless process. So for those that never heard about it, don't worry, we're not going to go into too much details here. But basically, it's a kind of stochastic process that uses two parameters that are either called lambda or mu or birth or death. In this package, they're just simplified to speciation and extinction because they're equivalent to speciation and extinction rates. And you can just create this. Don't worry if you don't know what set seed mean. It's just for repeatability of random generation, but it's not very important here. But to specify your parameters, you use this function called make.bdparams. You'll see throughout the package, there's a lot of functions called make.something that helps you generate basically some modular elements in the package. So let's create here a speciation parameter that has a speciation rate of 0.5 and here a speciation rate of 1. So the bigger the number, the faster speciation happens. The smaller the number, the smaller speciation. So, and then you can feed this Birthless parameters to your trees function. So here you have this generates a small tree. This should generate a big tree. And let's see what that looks like. Yay, this is a small tree. And poof, yay, this is a bigger tree. Actually, this one reached the stop rule of 200 tips rather than timing in 4. But yeah, so this is the basics on how you can change the parameters for tree generation. And just want to kind of explain what's happening inside here. Basically, these objects here, so for example, this object we created from this line here called speciation. Whoops, we were here, speciation 05. This is an object that's called treats, that's of class treats and BD params. We're going to see these subclasses, these treats class objects throughout the package. But basically what it does is it can, so it does internal checks of whether this object has the good formatting to be passed to treats and stuff. But also you can always print it to ask what's in this object. So for example, if you call it just test, which I very often do, you want to remember that test is actually here a tree's Birthless parameter object that has a speciation rate of 0.5 and an extinction rate of 0 because we didn't specify any extinction. And that leads to, let's specify the extinction parameter, so the death parameter. Let's do 1 year where we create this Birthless object with a extinction rate. So it's the same as for making the speciation rate, just type extinction equals, in this case, 0.1. And let's make one with a higher extinction rate. See here, I didn't specify speciation equals 1. This is because speciation equals 1 is the default value. So if you print the object, still say speciation is 1. Yeah, that's the default. And extinction is 0.5. This is what we specified. And then you can simulate your trees. So this is a tree with few fossils. This is one with many fossils normally. And you can visualize them. There you go. This is a tree with some extinction. So you can see 1 fossil year, 1 year, 1 year, etc. And this one should have many more extinctions. Wow, fossils everywhere. Very good. So this is how you change basically your birth and death parameters. Again, there is a lot of package that can do that already. But here there is already starts of modularity because here I've put just single values. So for example, extinction equals 0.5. But you can put multiple values or even sampler functions. So for example, this function here, runif, is basically a function that randomly samples from a uniform distribution. And you can basically create a Birthless object where your speciation, instead of being a fixed value, here is going to be a random value between 0 and 1. And every time you build a tree, it's picking up a value from this distribution. You can also just provide different values. So for example, you want to have speciation rates, I don't know, of 0.2, 0.3, and 0.4. And this creates an object where basically every time you simulate a tree with this object, it will randomly pick any of these values. So yeah, that's for the modularity bits here. There's some more options here I just want to get into before we start simulating some traits, is that sometimes you have choices of parameters that are not very optimal. So in this case, for example, we're going to specify, again, speciation rate of 1, which is pretty standard, and a very high extinction rate. So this is very close to the speciation rate. And what that can end up doing is basically generating a tree where all the species go extinct earlier than what you required through your stop rule. This is a dangerous example where here it will tell you an error message that it didn't manage to build the tree you wanted with your parameters. So basically your tree died before reaching any stop rule. This is fine. Error messages are very useful in R, and in the treats package, I try to make them relatively verbose to explain what's going on. But sometimes, for example, if you're doing loops or using clusters or etc., you might not want error message. That's fine. You can just use this option null.error equals true. So this will, instead of printing an error message, just return no if the tree didn't work. So again, in some cases that can be useful. But even more useful than that, instead of putting true for this option here, null.error, you can put a value here, let's say 100, and this will make the algorithm try at least, up to 100 times whether it can just generate a new tree until it reaches the stopping rule you wanted. So for example, here it's going to try up to 100 trees with the parameters you wanted. And here, just adding verbose equals true, just to see every trials happening. So this is this. Here it tried, so each dot corresponds to a trial, 1, 2, 3, 4. It tried 4 times before getting this tree that's not dead. Woohoo! It's a tree with, should have a lot of fossils in it. Let's see. Yes, so this is a tree with a lot of fossils that reach the stopping rule that we required. So that's it basically for how to simulate just plain trees. As you've seen, we've not generated any traits yet. Yeah, this is basically for the first aspect of the package. If you have any thoughts or questions on that, feel free to put them in the chat. I'm gonna have a glug of water. And yeah, if everything is quiet, I can continue on explaining how to add the traits. So that's the second part of the package, so the trees and the traits. So to generate the traits, it's the same way as we had this function make.birthless. We're going to use this function here called make.traits. To generate traits, you have some traits that are already implemented in the package. So these are the classic, your Brownian motion, your Ornstein-Uhlenbeck, etc., etc. There's a list of these traits in the package manual. But yeah, I just want to explain briefly how they are designed. So you basically need to create a function that creates a stochastic, basically continuous process. This is a Markov chain, basically, where every new generated value depends on the previous value and some kind of standard deviation, or in our case, some kind of branch length. So the longer the branches, the more evolution happens, for example. And here, this is a simplified Brownian motion process, where this function here, rnorm, this is from the base R package, is just randomly drawing a number from a random normal distribution. Here, n equals 1 is we want to draw one trait value, but if you want your trait to be 2-dimensional, you can change this value. Here, the mean here is this kind of encoded x0, that means previous value, and here, let's say, the standard deviation increases with the square root of the branch length. So the longer the branch length, the more you're likely to draw a number that's away from your previous value, which is the mean here. So again, don't worry if you don't understand everything about how to create these traits here. A lot of them are already pre-implemented in the package, so you can just use the one. So for example, this one, BM process, is one from the package directly. You can just use this one. But basically, you feed this this function that you've created to this function make.traits. Here, of putting also, you have many options in the function make.traits. I'm not going to cover them, but here, for example, I put a starting value of 0. Why not? This is actually the default. And this creates, again, this dual class thing, treats, and here it's a traits object that you can at any time print. So here it tells you this object contains one trait with one process. So the process here is a Brownian motion process. That's called by default 8, but we can change the name with one starting value. Let's change the name here. For example, you can give this trait name equals BM, for example. And now if you just print your object, it says, okay, one trait for one process that's called BM with one starting value of 0. And this is exactly what I have here, doesn't matter. And nice thing with this traits object is because you design your own functions, etc., you can always visualize what they look like in a non-birthless process. So this is just a Brownian motion where we basically, the function has just simulated that by just randomly drawing these values. And this is what happens over time. So if you do if you want to look what's happening with another trait, so let's do OU, for example, process equals OU process. This will just quickly visualize what OU process looks like. Very nice. Maybe not useful, but it can be good for just visualizing what's happening. But again, there's no tree simulations. Also, all these functions make.something in the treats package are actually internally testing what you're feeding them. So if you make any mistake, so for example, this is a process that's badly formatted, it will tell you an error. This doesn't work because of these reasons. So don't worry. The idea here is you cannot break the package or you will not run up into problems later in your simulation because all these things do pre-checks. But with that in mind, again, we can feed that to a treats function that now has stop rule. You know what that means. Birthless parameters, again, you know, and now you just feed these traits here. That was your traits object. And again, no error, etc. It's just to simulate multiple trees. And let's see what that looks like. Just go this. And ta-da! So this is not the nicest tree I've ever seen, but basically you can see it starts from the starting value 0, and then by chance it got into positive values, and then it's a Brownian motion from there with some extension peppered throughout the tree. So that's that. Though one thing now is this object from treats that's called, so previously we've just generated philo object. This is now a treats object, and the treats object basically contain two sub-object. One is that you can access using $tree is the philo object, so that's the tree. And another one is the data. So this is just a matrix. Let's see. So this is your philo object, and this is your matrix. Here it retained the train name. So here, you know, it's a Brownian motion. This is the first node, N1 has a value of 0 because we specified that, and these are all your other values. This is the, oops, sorry. Let me just show the full table. This is the full trait table. Of course, you can simulate traits in multiple dimensions. Then you'll have multiple columns, and again, one row per species. Oops. This is just same tree with the trait. So that's again pretty. Hopefully, it's pretty straightforward, and you can basically then just basically, this is the where the modular aspect starts to kind of appear, where you can change easily your trait by having multiple traits, objects, etc., and easily change them. Another kind of little bonus here that some reviewers requested that I think was really useful is to actually map. So instead of generating a tree and a trait, you might already have a tree and are just interested in generating a trait over that tree. So here we're going to see this example is, So this data, bird order, is an inbuilt data in the 8 package, and it's basically just, let me plot that. It's just basically a phylogenetic tree with all the bird orders, passeriforms, yada, yada, yada. So you have some speciation or like splitting happening here, and then very long branches here. Beautiful. And you can basically, if you already designed a trait object, you can just plot or like map this trait to simulate a trait value using your trait object that's here on your tree using the MakeTrades function. And you end up with a treats object that has your data and your tree. Plot that. Ta-da! So here's a Brownian motion mapped, simulated on this bird tree. So again, you see this like cluster of speciation here at the start, and then these very long branches leading to the bird orders. So this is actually an interesting point here because of course in this bird evolution, we know that it doesn't go from a node here 20 million years ago and then nothing happens until it reaches like trait doesn't change or change in a linear way, for example, until it reaches the living species. So you might be interested in actually simulating what's happening along the branches. So this is another option, kind of bonus here. It's called save.steps that basically allows you to create singleton nodes. So what I mean by singleton nodes is nodes in a tree. So most nodes in a tree connect to one ancestor in the future and two either tips or nodes in the future. Singleton nodes just connect to one ancestor and one node or tip. And you can basically generate these nodes along a branch here, for example. So let's show here. You can use this option here, save steps, with a value here. Year 0, 2, it means every 0, 2 time units, it will save a trait value for this simulation. You can also just specify different values, like you can say vector values. So you're interested in simulating that at time 0 0.2, 1, and I don't know, 1.5, and this will just save 3 steps. But yeah, I want to show the example saving multiple steps. Oops, and this is a continuous trait, and you can just plot that. Ta-da! So here you have then another tree with traits, and again you see here this starting value here basically connects to this basically singleton node that connects to this one, that connects to this one, etc., etc. And if you wouldn't have saved all these steps, this will be just a straight line connecting from this dot to this dot. So this is a way to kind of record the simulated evolutionary history along the branches. And so that's pretty much the basics with some trees and generating trees and traits. And now I just wanna kind of tell you about a last kind of class of objects that are modifiers here, and we kind of gonna have a break here talking a bit more about the Birthless process, because again, the idea when I designed this package was that it should be super modular. So not only can you change your parameters of like speciation and extinction, or your trait processes, the number of traits, the number of dimensions, the correlation, etc., but also you should be able to easily modify the Birthless process itself. So let's have a look. So if you're on here, there is this link here. Where I'm going to go now shows basically how the Birthless process is implemented in the treat package. So in here, this is just a visualization of the algorithm. Let's say we have already generated some part of the tree. The algorithm goes in 4 steps and just repeat these 4 steps until reaching a stopping room. The first step here is select a random lineage among the ones that are live. Let's say here it's selected A. For those that are a bit more nerdy or advanced in R, you can click here and it gives information on what's actually happening in R. For those that just like visualizing, this is what's happening here. First, we select a random lineage. Then next step, we just generate some branch lengths. So here we generated a random branch length of length 1. Again, for the nerds, you can see all the details on how it works in R and in math in this thing. And you basically apply this branch length to all the species that are currently alive. Then next step, you can generate a trait value. We've seen how that works. And then next step, you can choose where the algorithm randomly choose where the lineage that you've selected goes extinct or speciates. In this case here, we speciated into two new lineage, D and E, with no branch length for these two lineages. Again, here's how the math work. Then you go next step, which is back to the first step, select a random lineage among the ones that are currently alive, then add some branch length to everything that's alive, then simulate some trait value for the species that is the lineage that's selected. If you had, for example, the safe step option, it will simulate trait values for everything. Then again, choose whether you go extinct or not. In this convenient example, our lineage B goes extinct. And then step one again, select a lineage among the ones that are alive. So B is now dead, so it cannot be selected. Again, grow some tree length for everything. And then repeat. At the end of the algorithm, for all the species that are currently alive, it will also generate a trait value. And this is how you get your tree. So again, remember, it's these 4 steps just done one after the other. And this is the algorithm. So here I'm going to talk a bit more on how you can modify these steps, because again, I have not shown in details the math and the algorithm on how these steps are done, but you can, so for those interested, you can read in more details here, but you can basically relatively easy modify them using this new class of object that's called Modifiers object. So let's say we want to modify the speciation whether a lineage goes extinct or speciate. We want to make that so in the current algorithm, which is the correct Birthless, the default Birthless algorithm. This is basically this whether a species go extinct or speciate is basically based on your speciation and extinction rate. Let's say we want to modify that and make this like density dependent. So we can make we can basically modify this rule so that instead of just looking at the speciation and extinction parameter, it also looks at the number of lineages that are present in the tree. And we could simulate some kind of scenario where, let's say, the environment that you simulated gets saturated with species. So the more species there are, the more likely species are going to get extinct or something like that. So the way to do that is you can, again, create a function here. So the best way is to copy paste things or go in the manual where there's a lot of information, default function, templates, etc. But basically this bit here, so this is called the turnover ratio, doesn't matter, is the same bit as here. And we can just take this bit here and modify it by making it dependent on the number of lineages. So here is divided by 10. So 10 is multiplied by 10 divided the number of lineages. So that means that this, so if there's less than 10 lineages, this number will be always small or big, never remember. So that means that speciation will always occur, and the more lineages appear, the more this basically ratio will be smaller, I guess. Again, never remember, but basically the more extinction will occur. So you can do that if you create, again, this like density dependent speciation scenario. You can feed that to this function MakeModifier, and here you want to modify the speciation element. So again, these 4 elements that are selecting a species, growing some tree lengths, speciating or going extinct, and generating traits. You can create that. Again, this is this treats class where you can visualize what's in it. So it's the default branch links process because we didn't change it. Default selection process, but now our speciation process is set to our function density dependent speciation. And we can see what this looks like. So this is the first example with no modifier. And this is our second example with the modifier. So to feed the modifier, Same, your treats function, just give it modifiers equals the name of your modifier. And let's see what it does. So this is our tree without a modifier. We've seen some trees like that. This is using the same parameters as before. And then let's see the same with the modifier, where basically you see early in the tree history, there is no extinction happening, even though we use the same extinction rate here of 0.5, for example. But like speciation increase and accelerates basically the more species there are in the tree. So this is just kind of to illustrate how you can relatively easy change the birthless rules or the birthless processes in the treats package. And just to finish, basically, I have been talking a lot about the manual. So this is an online resource that if you go on the GitHub page, you can easily find. But I'm just going to show you. So another class of objects is called events. But instead of going into examples on how to make them for people that want to redo the workshop, there's a lot below here they can do. I'm just going to show some examples because it's the same. You just have to basically configure it. Your function for your special extinction event, etc. I'm just going to show you here a bit more how the manual works, so how you can find resources. And here is just showing a gallery of extinction events if my internet works. Okay, I don't know why it's so slow. Let's just go straight to the manual. So this is the treats manual. If you want to find it, you just go on the GitHub page, and it's the first link here. How does it work? You have the detailed manual. And if you go in the last section here, you have some specific examples of extinction events. Do I need to scroll down? Is my internet completely dead? Oops. Sorry, I think maybe it's because lots of people are clicking on the manual. It's a bit slow to go there. Let me see if I can open it. Oh, no, here we go. We're here. Okay, cool. So, but ignore that. I mean, don't ignore it. Read it if you're interested in more details, but for now, ignore it. Yeah, I'm just going to talk through some extinction scenarios that you can easily simulate. Can I make this bigger? No. Good. Let's make it a bit bigger so it's comfortable for everybody. So here, for example, you can do a random mass extinction after some amount of time. This was in the no example I showed before. This is basically how it works. This is how you configure in like 4 lines. You can configure your mass extinction event, give that to treats with this new class here, events equal mass extinction. And here you see 75% of species go extinct at time unit 2, for example. This is another one where, again, this kind of shows how the example is relatively easy to code. And you can have here, it's an extinction event that happens after at time unit 1, and all species with negative values go extinct. This is what's happening here. You can do some other ones here. I think it's the background extinction rate that increases after some time. Here's speciation rate that decreases after some time. Here's no event. This is with an event. Here, this one is funny. You can change. So the extinction process can basically modify anything about your treats object. So your traits, your speciation and extinction parameters, your modifiers, even a treats object itself. We're going to see that later. This is where the modularity really shines. Here, for example, this is Brownian motion. But we say after time unit 1, this Brownian motion becomes OU motion. Poof, see a decrease here. This one does what? This is the example I've shown before with the change in correlation. Whatever, this is here, you loosen the correlation after some time. This is the one I showed at the start of the workshop. Yeah, this event it is whatever extinction for negative values. I don't know, I didn't read there. Okay, it's increased extinction rate for species with negative traits. This is this. You can change branch length here when reaching a certain number of taxa. Your basically waiting time is increased. And this is kind of, this last example here is to show the modularity of it. So these events can be treats objects themselves, which are called founding events. But basically, this here is simulating treats objects, so simulating a tree within a tree at some point. So this tree here in yellow is basically, so this tree in black here has some extinction rates. You can see here, and this tree in yellow within it is just a lineage or a clade that has no extinction rate. For example, you can do the same here. For example, I think it's hard to see here, but basically at some point a subtree is generated with a different trait process. So I think here it becomes a OU. So the whole tree is a Brownian motion, but one clade within this tree has a trait that evolves under OU process, etc., etc. So one thing for all these, this was also suggested by reviewers, that was really cool. I've basically started to create a gallery of all these examples of specific scenarios that you can find here in the issue button on the package, GitHub package page. And basically here is tagged with this simulation templates. You basically get these code that tells you that are in a kind of pre-formatted template where it says what it's using, what kind of function it's going to be calling. And you can basically have examples here that you can just copy paste. This is for making the Christmas tree. So you can see the Christmas tree was a kind of more complex example, but it's again, not that complicated to generate. And if you just copy paste that, you should just get a Christmas tree. You can just browse in the gallery. The idea here is that I will continue adding some examples here, but hopefully some users, so maybe some of you are interested in also adding your own simulation templates and sharing them with everybody. So that's that for me. Hopefully there's time for questions, and hopefully it was clear and enjoyable.
Thanks, Thomas. That's great. So I mean, if anybody's got any questions and wants to put their hand up and then unmute themselves and just ask the question, that's fine. If you prefer to type the question, please do that. I will leave people typing. So I'll kick off whilst we're waiting. So what are the sort of top 3 things that you're planning on implementing in this next?
Oh, very good question. So I do have them. So I want to do more things with discrete traits. So more simulation with discrete traits, which is a relatively easy. I think I have a wish list here. Again on the, yes, so if you go on the news thing, if you go in the raw version, I think there is some all these hidden kind of things are some suggestions that people have made and that I want to add, so bug fixes and everything. But the main ones is, yeah, I want to work more to simulate some like paleo data, basically. And another big thing is basically with all these, as I've been showing for mapping trees on traits, you could use that for doing ancestor states estimations. But instead of just estimating ancestor states using, for example, most packages use a default Brownian motion, you could basically use any trait object you want. So yeah, I want to work more on ancestor state estimations and discrete things, and that's the top 2, not the top 3. Sorry.
Top two is good. I was just trying to give you a long question that gave you people to type. So Will has a question. So he says, "Great talk, Thomas. Can you implement trait-dependent extinction and speciation?"
Yes, totally. So basically, in the algorithm, you can make your extinction and your speciation depending on either the trait value of any tip. So whenever it's evaluating something, so whenever it's doing the selection part, you can either make, for example, extinction or speciation more likely if the tip has a positive or a negative value, or you can do that depending on the tip ancestor value, or you can even do that. This is a kind of cool way to simulate some kind of trait space occupancy where species kind of try to separate them each other. So you can make, for example, species that have traits trait values that are close to other species more likely to go extinct, and species that have traits that are more rare in the trait space more likely to speciate, for example. So yeah, that's yeah.
Cool. Okay, Zhao has a question. So he says, thanks very much, Thomas. Amazing talk. I have a question. How would you simulate speciational or punctuational evolution using treats?
That's also I love these questions because basically it makes me want to play around and code this scenario. But basically, you could make rules. So if you want to do like a punctuated equilibrium type evolution thing, you could probably generate like branch lengths for like you can make your speciation events and your growing branch lengths part of the Birthless process. Just basically, you could like say that for like this kind of punctuated, so this kind of plateauing evolution part of your evolutionary history, you're not likely to have speciation events, and then you can encode that like, let's say after some specific branch length growth, then speciation events are extremely likely, but just for a short period of time. And then again, it can slow down and etc. So this should be relatively easy to do by modifying these modifiers objects.
And then John has a question as well. So he said he was going to ask about discrete traits. Is there anything you can do with discrete traits now, or is it just something you're going to implement in the future?
No, so there is now in the pre-implemented traits, that's one that's called discrete process. I think that's it. So if you just do / discrete process, my R manual is not very useful, but here you can see if you just look at the in our documentation for this trait process generic functions, you have here a list of processes, and in there is, I thought there was a discrete one. Yeah, we got here. There's a discrete process where basically you give a transition matrix for like basically the likelihood of going from trait state 0 to trait 1, or you have 20 trait states, and this is just a bigger matrix. And basically, then the longer the branch length, the more likely you are to change trait value, trait state, for example. And yeah, so it should be also very easy using this discrete process implemented function, yeah, for now.
Great. And then another one from Will. If there's time, so bifurcating speciation seems to be a core part of the birth-death process. Any plans to allow for budding speciation?
Definitely. I think I'd love to add it, but I think it's I'm always thinking because in a way budding speciation can be either seen as, you know, one lineage being constant and one speciation, so like a budding event coming from this tree. I think when you're simulating both trees and traits, this becomes more obscure. So you could have, for example, one lineage that has low variance in trait change. So basically in these kind of, tree like time and trait plots, you would have just like one lineage that basically it looks like it's speciating, but one side of the speciation stays the same, let's say, as the ancestral value, and the other side of the speciation is the budding that like gets a different trait value. So this is possible to do now, where you could like choose left or right of the speciation that has different properties, for example, for the trait value speciation. But maybe, yeah, it's probably a good idea to implement that properly and have a rule that's called just budding rule, for example, and then all the speciation or some amount of the speciations happen with a kind of formal budding process.
Cool. And then I think this might have to be the last question, but this is just a clarification from Zhao, who was asking about punctuational, sorry, let's just check. Talking about, yeah, speciation or punctuational evolution. He's just asking, what about simulating trait evolution when the change occurs at the speciation event?
So that means that, like, for example, when the speciation event happens, some different rule of speciation or extinction or trait changes. Is that right? Yeah, so basically, again, this is doable with the latest example that I've shown, where it's like super intricate and modular thing, where basically you can, each lineage that you create, so each speciation event can itself be a treats object. So can be basically a simulation that has its own Birthless parameter, its own traits object, its own modifiers, etc. So that's a bit longer to script, but it's totally doable that every speciation event, for example, you have your specific rules, or you can do when there is a speciation event, there's more likelihood to change rules, but you can keep the former rules, etc., etc.
Oh, yeah, perfect. So I think if anybody has more questions, Thomas, I'm sure Thomas will be happy to chat via email or via GitHub issues. Or, you know, if you see him in person at a conference over the summer. But yeah, so massive thanks to Thomas for presenting for us today, and thanks everybody for coming along. Hopefully you'll come to some more of these. Also, if you are writing a methods paper at the moment, or if you have published one in the past and would like to run one of these, do just drop me an email. You know, we're very happy to have these, even if they're papers that were published a little while ago. So hopefully see you all at the next one, and thank you very much, Thomas.
Thank you very much.